Laplace transform is a tool which is used to convert signals from time domain to frequency domain. Actually, we have two types of Laplace transform: bilateral Laplace transform and unilateral Laplace transform. But here, we will study only unilateral Laplace transform. Obviously, you have to study both these types in great depth in signals and system. In order to transform a given function of time, ft, into its corresponding Laplace transform, we have to first multiply the function ft by e minus st, where t is time and s, which is a complex variable, which is equal to sigma plus j omega. Sigma is referred as damping factor and omega is the angular frequency. J is the imaginary complex number, which is also referred as iota. We have to integrate this product with respect to time with limits from 0 to infinity. This integration results in Laplace transform of the function ft, which is denoted by fs. For example, we will find Laplace transform of unit impulse function. We know the unit impulse function has value only at t is equal to 0, otherwise its value is equal to 0. Therefore, we can change the value of integration limits to 0 minus to 0 plus. By this expression we can say we are interested only in the value at t is equal to 0. E raised to the power minus st will be equal to 1 at t is equal to 0. Now, the Laplace transform will be equal to integration of unit impulse function from 0 minus to 0 plus. We also have the property that the value of integration of unit impulse function from minus infinity to infinity is equal to 1, and we also know that its value lies only at the point at t is equal to 0. Therefore, the value of this expression will be equal to 1, giving us the value of unilateral Laplace transform of unit impulse function to be equal to 1. Similarly, we can find the unilateral Laplace transform of other very simple and common signals. These are unilateral Laplace transform of some very basic signals which you must know. Now we will see some properties of unilateral Laplace transform. You should keep in mind the properties of unilateral Laplace transform and bilateral Laplace transform are quite different, and that's why it creates sometimes confusion. Just keep that in mind while writing short notes. The first property is Laplace transform of linear combination of two separate functions f1t and f2t. f1t and f2t being multiplied by constant a and b respectively. The unilateral Laplace transform of this combination will be simply a times the multiplication of Laplace transform of function f1t plus b times the Laplace transform of function f2t. Suppose that we have function ft which has unilateral Laplace transform fs, then the unilateral Laplace transform of differentiation of function ft will be equal to sfs minus value of function ft at t just before 0. If the function ft is differentiated two times, then its unilateral Laplace transform will then be equal to s square into fs minus s value of function ft just before t is equal to 0 minus value of derivative of function ft just before time is equal to 0. The same sequence will continue if we have to find the unilateral Laplace transform of further derivatives of function ft. Obviously, before teaching I was a student myself, and I am quite aware that this property will not be very easy to remember. If you observe carefully, then to find the Laplace transform of nth derivation of function ft, we still have to find n-1 derivatives of the function ft. For reference, take the expression for unilateral Laplace transform of third derivative of function ft. In this expression, we still have to find the second order derivative of function ft. The other important point is, besides the first term, all the terms are negative. Coefficient s is having different powers but are present in a very simple sequence. For the nth order, you have to start with the nth power and afterwards decrease it by 1. The third property is of integration of function ft in time domain. If we are supposed to find the unilateral Laplace transform of integral of function ft, then it will be equal to Laplace transform of function fs divided by s plus the value of integral of function ft just before t is equal to 0, the whole being divided by s. Here also we have a regular sequence. If we have to find the unilateral Laplace transform of nth order integral of function ft, then still we have to find the value of nth order integral of function ft just before t becomes equal to 0. Here all the terms are positive and the power of s is little different compared to the expression which we got for differentiation of function ft. In the expression for differentiation in time domain, the variable s was being multiplied with different terms, but here the different powers of s are dividing the different terms. Here the power or different coefficients of s is little different than the expression we have seen for differentiation in time domain. Try to not get confused with these two properties of unilateral Laplace transform. In future, it is very possible for you to forget or get confused within these two properties of unilateral Laplace transform. The one is differentiation and the other is integration in time domain. If we multiply exponential plus minus at, where a is any random constant, then its unilateral Laplace transform will be equal to function f s plus minus a. Similarly, the unilateral Laplace transform of function ft multiplied by the time t is equal to negative of differentiation of function fs with respect to s. The next property is initial value theorem. If we assume a function ft whose value is 0 for all values of t smaller than 0, then we can find its initial value which is at t is equal to 0 from its Laplace transform also. For that we have to first multiply its Laplace transform with s and then find its limiting value when s tends to infinity. Initial value theorem is having some limitations also. First, we have already seen that the value of function ft must be equal to 0 for all t smaller than 0. The other limitation for initial value theorem is in frequency domain, which is the expression for Laplace transform of fs must be strictly proper, meaning that the degree of numerator should be smaller than the degree of denominator. Few examples are shown for strictly proper Laplace transform and improper Laplace transforms. The next and the last property is final value theorem, as per which we can find limiting value of function ft from its Laplace transform. For that we have to first multiply the Laplace transform with s and find its limiting value when s tends to 0. Here also we have one limitation, which is the roots of denominator of sfs must have negative real parts. If they are positive or 0, then the final value theorem is not valid. An example is shown where the denominator is having a positive real root, and that's why the final value theorem is not applicable. When you will be studying these things in signals and systems, then you may get to know why this happens. Actually, the roots which are having positive real root are increasing functions in time domain. And how can you tell a final value of a function whose value is constantly increasing? The functions which have negative real root are decaying functions whose value saturates to a particular value, whereas the functions which have imaginary roots are oscillatory time functions whose value goes up and down within its maximum and minimum values. The most common example is of sine and cos functions whose values keeps on fluctuating between -1 to 1 even if the time approaches to infinity, but still you cannot tell what will be its limiting value when time tends to reach infinity. Such systems whose value oscillate between maximum and minimum values are referred as marginally stable systems. By remembering the unilateral Laplace transform of some basic signals and remembering all these properties, we can find Laplace transform of a variety of signals. Signals in a system as well as control system, both these subjects are numerical type subjects demanding good practice of solving different types of problems. If you are trying to memorize these properties and Laplace transform by writing again and again, then this will not help you for long run. You have to solve a lot of questions to remember these things.